We've seen non-determinism before. Basically, non-determinism is magic. So when we talked about non-deterministic finite automata, the idea was that this automaton is again magic. It somehow magically knows which path to take. So whenever you want to run your automaton over a particular input, it can have many different runs, but it accepts even if one of those runs accept. So now let's add non-determinism to our Turing machines. So we had this concept of a Turing machine, and we said that it consists of all of these things. So the main difference with a finite automaton is that I now have an infinite tape. So I have as much memory as I want, but I still have a finite set of states. And again, the intuition was that my states kind of correspond to lines of code. So if I'm writing a C++ code, I'm not going to write an infinite code, right? So I'm going to have a finite number of states. I have an initial state, I have a transition function, and this was very much similar to the automata. The only difference is that it's much more expressive now. So it reads the current state of my automaton as part of my Turing machine. It reads the current entry on the tape. And based on that, it decides where to go. It decides what the next state is going to be. It decides what to write on the tape. And it also decides whether it wants to go to the left or to the right. Okay, so now non-determinism is all about this transition function. So the only thing that I'm going to change if I want to have a non-deterministic Turing machine is the definition of this transition function. So I'm going to keep everything else the same. And I'm just going to say this. I'm going to say previously, whenever I had a state and a tape entry, I basically had only one action. Based on my current state and tape entry, I had a unique choice, a deterministic choice of what the next state is going to be, what I'm going to write on the tape, and whether I'm going to go left or right. Now, imagine that instead of having a unique choice, I have many different choices. That would be a non-deterministic Turing machine. So this function delta, it's not going to give you an element of this set, which is just the next state and what you write on the tape and whether you go left or right. It's going to give you several elements of this set. And then the intuition is that, again, the Turing machine magically knows which one is better and takes the best possible outcome. Okay, so this is going to look a little bit weird, but basically, instead of having this whole set, I'm going to have this thing mapped to subsets of that. Right? So whenever I have a transition, I don't just have one state that I can go to. I have a subset of states, and I can go to any one of them. That's how you will have a non-deterministic Turing machine. And again, all of the things before are the same. So this is going to be your next state. This is what you write on the tape. And this tells you whether you go left or right. The only difference is that now you can have many choices. You don't have a unique deterministic choice. It's non-deterministic. You can have many choices. Okay, that's how I define a non-deterministic Turing machine. And another way of looking at non-determinism is to look at everything as basically, let's say, a state machine. So if I have, for example, a deterministic finite automata, what are the states that my machine can be in? They're literally just the states of the automata, right? But if I have a Turing machine, in order to tell you exactly what state my Turing machine is in, I have to include the tape. I have to tell you which state of Q it's in. I have to also tell you, yeah, those are the only things, yeah. I have to also tell you the head position, right? So 3 things. So you can think of a Turing machine as a graph, an infinite graph of the Turing machine states. And I'm using the word state not just as the states in Q, but as all the possible states of the Turing machine. I don't have a better word for it. Sorry, I'm just calling both of them states. But basically, you can think that I have an infinite Turing machine. And the idea is that every vertex of this graph, which is my state graph, is going to tell me this is what's on the tape, This is the index that I am on the tape. And this is the state that I am in my small automaton inside my Turing machine, right? And then in this graph, I have a bunch of transitions, and this is the role of my transition function delta that tells me that, for example, if you have T on your tape and you're at index I and you're in state Q of the machine, maybe you can go to T prime, I plus 1, and state Q prime. Okay, so I can create a huge graph, actually an infinite graph, that has one vertex for every possible state of my Turing machine. And the intuition is that my Turing machine is deterministic if in this huge infinite graph, every state has at most one outgoing edge. Of course, there are states where there is no outgoing edge. For example, the states where the Turing machine is terminating, right? And it's non-deterministic if I have a situation like this, so that from one state, I have a choice. I can go to this one or I can go to this one, okay? But at the end of the day, it's up to you how you want to imagine non-determinism. This is the formal definition. The formal definition is that you get several different actions. You get a subset of actions and you can do whichever you want. Okay. Now, why do we care about non-deterministic Turing machines? For the same reason that we care about non-deterministic automata. Some problems are easier to solve if you have non-determinism. Okay. So let's go and define some other things. So let's say I have a Turing machine. How can I formalize the runtime? Well, we've talked about this before. Given any particular input, and we write our input on the tape, the runtime of my Turing machine is the number of steps that it's going to take until it terminates. Okay. Now, this made sense for a deterministic Turing machine, because a deterministic Turing machine with an initial state and an initial tape has exactly one possible run. And then I could say, in this run, how many transitions did I have? How many times could I apply the function delta? Okay. But what happens in a non-deterministic Turing machine? What is the runtime of a non-deterministic Turing machine on a particular input? Well, I can have many different runs. Let's take the maximum of all of them. Or if no maximum exists, then I say my runtime is infinite. Okay. So you can define the runtime for your non-deterministic Turing machine. Generally speaking, I say this: given a Turing machine M and an input X, the runtime of M on X is, well, I'm going to show it with T of MX. Sorry, big M. And this is basically just going to be the number of times that I apply the delta function until I reach one of the terminating states, assuming that X was written on the tape initially. So if X is initially written on the tape, how many steps does the execution take? How many times can we apply delta until we reach a terminal state? Okay, nice. And again, I said that if we have non-determinism, I just take the worst case scenario. I just say among all the runs that are possible over this particular input, what is the maximum time? Okay, but now how do I actually define memory usage? How much memory does my algorithm use? Well, I have a tape and my tape is infinite. But if I'm going to terminate in finite time, I'm not going to see everywhere on that tape, right? So if I'm terminating in finite time, I'm definitely only seeing a finite number of different slots on that tape. I cannot read all of it. I cannot write to all of it. So I can just count. I can say, what is the farthest I will go in my algorithm on this tape, right? So my algorithm always starts with the head being at position 0 of the tape. So how much does it go to the right? How far does it go? That's going to be my memory usage. And this gets back to the arguments that you've seen over and over in this course, where I constantly say you have to read the input. And so your runtime cannot be less than the size of the input. What's the reason for that? Because if I have my input written on my tape, I have to go over the whole tape. And as soon as I go over the whole tape, that's my memory usage. I have used that much memory. Okay, so here's what I'm going to do. We actually call it space for historical reasons. We don't call it memory. So the space usage of the Turing machine M on input X, and we show that with S of M and X, is the largest index that would ever be accessed on my tape if I run M with input X. So if X is initially written, what is the longest, or what is the largest index I of the tape which is accessed by M? Now, very importantly, my space usage is always less than or equal to my time. That's by definition, right? Because if I'm moving to the right, every time that I'm moving to the right to access the next state in the next slot in my memory or in my tape, I'm definitely using 1 unit of time. I'm using 1 transition. So I will never have a situation where my space is bigger than my time. Now, of course, there are other definitions where you can have more space usage than time usage, but in this particular model of computation, we always have S of mx is less than or equal to T of mx. Okay, now again, what happens with non-determinism? I just take the maximum. Okay, so if I have several runs, what is the largest index that is reachable by any of the runs? That's going to be the space usage. Okay, great. But now we go back to lecture 1 of this course, where we said that we want to analyze the runtime of algorithms and also the space usage of algorithms. Actually, let me just call it space instead of memory, because that's what most folks use. So we want to analyze the runtime of our algorithm based on the size of our input. But now the size of our input is very well defined, because if I have an input X, how many slots in the tape does it take to write X? Of course, it also depends on my alphabet, but let's say my alphabet is just 0, 1, and blank. Okay, so with this assumption, what is the length of my input? So now I can again define worst case runtime. So I can say the worst case runtime of a Turing machine M on inputs of a particular size, on inputs of size N. I'm going to use T again. Don't get confused by that. So I show this by T of M comma N. And this is basically going to be the maximum runtime of this machine over any input that has a size of N. So the maximum over all inputs X that have a size of N of T of Mx. I don't know why I write smaller. Okay. Lecture 1. Now, for the space usage, I can have a similar definition, right? So I can say worst case space usage is just S of Mn. And this is, again, the maximum possible space that I would use over all inputs of length n. Okay. Now, of course, we can go back and we can apply the O notation when we're analyzing the runtime and so on. But the important point is that we now have a very well-defined concept of time and a very well-defined concept of space. Now, this is not exactly the same formulation of time that we were using in this class, especially when we were talking about, let's say, graph algorithms. We were actually using the RAM model of computation, where the idea was that I can access any point in the memory in O1, right? So if you wanted to read from an array, you wouldn't have to scroll through every element of the array. You could just read it. So my notion of time right now is a bit different from the notion that we were using, but it's not different in the sense that anything that I could do in polynomial time, I can still do it in polynomial time, right? Because if I'm running my algorithm in polynomial time, I'm accessing hopefully only a polynomial amount of space. And now if every access needs me to scroll to that point and back, my runtime will only be multiplied by another polynomial. So it might be that your runtime in the RAM model is much smaller than your runtime in the Turing model when you have a Turing machine. But you will see that for our use cases, this usually doesn't matter. There are cases where it actually does matter, but there are rare. So we're going to use the Turing model for the rest of this course, which is literally just 2 more sessions. Okay. So the other issue I want to talk about is that we basically considered 2 different kinds of problems. We considered decision problems, where the idea was that I want to calculate a function that takes some input and either accepts it or rejects it. So my output is only yes or no. And we also had kind of more functional problems where I get a string as input and I give another string as output. Now, we want to focus mostly on decision problems because actually every other problem can be turned into a decision problem. Okay, so how is this? Well, a decision problem basically says something like this. It says, I give you some input, let's say X, and your output is just 1 bit. It's 0 or 1. Okay. Now, so for example, suppose that my input is a graph, and I'm asking you whether this graph can be colored using 3 colors such that every 2 neighboring vertices have different colors. So the answer is either yes or no. It's a decision problem. Now, of course, I could also ask you to give me a coloring. In that case, you would have to create an output. But I can convert that to a series of decision problems. How can I do this? Well, basically, I can give you an input, and I can also give you another index I in the input. And I can ask you, what is the ith bit of the output? So if you're giving me some output, let's say in my original problem, I'm giving you a graph, and you're giving me a 3 coloring of this graph. This 3 coloring is going to have a particular length, right? So for every vertex, you're just going to tell me, is it color 1 or color 2 or color 3? Now, let's say that the output is supposed to be k bits. Now I can change the problem where I just ask you, given this input to the original problem, is the first bit of output 0 or 1? And then you tell me if it's 0 or 1. And then I ask you, is the second bit of output 0 or 1? And so on. So if we can solve decision problems, we kind of can solve all the problems. Okay. Another thing that is very commonly seen is optimization problems. And so in an optimization problem, we usually have something to optimize. So for example, let's say that as input, I give you a graph. Okay. And as output, let's say I want you to output the size of its largest independent set. So the largest subset of vertices such that there is no edge connecting any two of these vertices. Okay. So output is going to be, let's say, the size K of a largest independent set. Okay. Now, this is an optimization problem because you want to maximize K. We can also have optimization problems where you want to minimize something, but this is a maximization. Now, how can I easily convert this to a decision problem? Of course, I can use the trick from before, like ask what is the first bit of K, what is the second bit of K, and so on. But I can also use binary search, right? So I can just say that in the input, I not only give you a graph, but I also give you some number I. Okay. And then in the output, instead of actually giving me the size of the largest independent set, you just answer me, is K, the size of the largest independent set, greater than or equal to I or not? Okay. Now, this is a decision problem. And if I have a solution to this decision problem, if I have an algorithm that solves this, I can just do a binary search on I, and I can find the correct value of K. Right? So for these reasons, we're going to focus mainly on decision problems from now on. But again, just realize that whatever I'm saying about decision problems can very much be extended to all problems because I can turn anything into a decision problem. Okay. Finally, we want to define P. So P is a class of problems. And intuitively, P is the set of all problems, and I mean decision problems, that can be solved in polynomial time. Okay. What do I mean by that? Remember that every decision problem is a language. Okay. So I say a decision problem L, which is again a language. It's basically just a set of strings, the set of strings over which I will return true. And it's of course a subset of sigma star. So it's a set of strings. A decision problem L is in P if I can have a polynomial time deterministic Turing machine that solves it. What does that mean? So if there exists, let's say, a Turing machine, M. So first of all, I want M to decide L. So M should output yes if the input is in L, and it should output no otherwise. Okay, so that's my first constraint. But actually, even before that, no matter what input I give to my Turing machine, it has to terminate. So first I say that for any input X, I want MX to terminate. So it doesn't run forever. Or another way of writing this is that I will have T of MX is less than infinity. It doesn't run forever, it's a finite number. Now, secondly, I want to say that for every X, if I run M on the input X, it returns 1 or true, if and only if X is in my language. Okay, so all these two are saying is that I have a Turing machine M, which solves the decision problem L. But that's not all I want. I also want to say that the runtime is polynomial. Okay, so I say that there exists a Turing machine M and a polynomial. Let's call this polynomial small p, and don't confuse this with big P. Okay, so the third condition I want to have is that for every input X, the runtime of my machine on this input X is going to be less than P of the size of X. Okay. Or another way of writing this is that I can say for every input size N, for every N, the worst case runtime of my machine on inputs of size N is at most P of N. Same thing, doesn't really matter which definition. Okay. So this P is a class of problems, right? So it's a class of languages or decision problems, which means that it's basically a set of languages. And a language or a problem is in P, intuitively speaking, if I can solve it in polynomial time. If I have a Turing machine M that solves it in polynomial time. Now, very importantly, this Turing machine should be deterministic. Okay. Now, sometimes people don't call this class P. Sometimes they call it P time because, well, it's obvious, right? So the idea is that these are the problems that you can solve in polynomial time. And as you can imagine, there is also the concept of P space. And P space is the set of all problems that can be solved in polynomial space. Okay? And here's something I can give to you in the final exam. Prove that P time is a subset of P space. Okay. It's actually pretty easy to prove this using the things that I have just taught in this session. Okay. No, it's not the opposite. P time is a subset of P space. Okay. But now let's go to NP. What do you think NP is? N stands for non-determinism. So it's literally P, except that my Turing machine can now be non-deterministic. So again, it's a class of languages, so I can just copy this definition that I had for P, and I can put it here. And okay, a decision problem L is in NP if there exists a non-deterministic Turing machine M that accepts this language or this decision problem in polynomial time. So everything is the same as before. It's just that I have the extra power of non-determinism. Okay. But now I'm going to give you a different definition of NP that only uses deterministic Turing machines because it's easier to reason mathematically about deterministic Turing machines. So I prefer not to use non-deterministic Turing machines in the definition of my class NP. Okay. Actually, before that, let's just talk a little bit about intuition here. What does it mean when I say I have a non-deterministic Turing machine that accepts this in polynomial time? It means I have a magic machine that can just magically make the right decisions all the time. Okay. So imagine that I can write C++ code, but I have a magical construct. I have an if where I'm not writing any constraints, any conditions for the if. I'm just telling the program, choose the right branch. Choose if you want to go to the then part or the else part. And my program magically always makes the right choices. So it always goes in the right direction so that it accepts the input if the input is acceptable by any run. Okay, this would be a non-deterministic Turing machine or a non-deterministic C++ program. Of course, this is just a mathematical construct. We don't have it in reality. It would have been great if we could program like that. Some people use ChatGPT as if it's a solver like that, but that's not how it works. Okay, so what can I do if I have this magical power? I can actually solve a lot of problems. So as an example, let's try the famous tree coloring problem. Okay, we will come back to this problem many times in this course. So my input is an undirected graph. Say G with vertex set V and edge set E. And my question is, can I color the vertices of this graph with 3 different colors such that every edge has 2 different colors on its 2 endpoints? So the output is basically this. Does there exist a coloring, let's say a function C, that maps vertices to 3 colors, 1, 2, and 3? Or actually, let's say red, green, and blue. Okay, such that for every edge UV in my edge set, the color of U is not the same as the color of V? That's the question. Now, as we will soon see, this is a really hard problem if you want to solve it with a deterministic Turing machine, deterministic program. And by the way, we've seen that C++ is Turing complete. So instead of actually giving you Turing machines, I'm going to give you C++ programs or pseudocodes. And you should just trust me that you can write these as Turing machines, right? Okay. So let's say that I have the power of non-determinism. We believe in magic. How can I write a magical program that solves this problem? Here's my magical program. Actually, should I write it in C++? Let me write it in C++. Let me see. Why doesn't this work? Okay. This is 3coloring.cpp. Unfortunately, of course, I cannot run this because we don't have non-determinism in real C++, but let's say I have it. So this is the situation. I'm going to have a set of vertices and a set of edges. So let's say I have a vector and it's a vector of pairs and these are my edges. Okay, and let's say I have some number n, which is the number of vertices that I have. Okay. Here's my function. I'm going to call it 3coloring. It returns true if I can color my vertices with 3 colors. Okay. And the colors that I have are R, G, and B. So let's say I have color, which can be R, G, or B. And then I have a color C n+1, let's say, so that I can assign a color to every vertex. Here's what I do. I say for every vertex U from 1 to n, magically assign a color to U. So I have this if with a star in it, and this is where I'm using the non-determinism. I say color of U becomes red. Else, if another star, color of U becomes green. Else, color of U becomes blue. Okay. What does this mean? This means that when my program gets to this if line, it can choose. It can go to the then part and set the color of U to red, or it can go to the else part, in which case it has another non-deterministic if. So it can again choose. It can go here and set the color to green, or it can go here and set the color to blue. And all of these are valid runs of my program. My program has many different valid runs. Okay, now at the end, I'm just going to check if this is a valid coloring. So I'm going to say for every edge in the edges, if the color of the first vertex is equal to the color of the second vertex in this edge, return false. So if I have an edge that has the same color on both sides, I'll return false. Otherwise, I'll just return true. That's it. That's my algorithm. It's a very simple algorithm. Again, if you have magic, it works because we said that it accepts, it returns true if there is any execution or any run of this non-deterministic program that returns true. So this program somehow has godlike powers and can decide how to do the coloring. Okay, now you see, this is also polynomial time. This is actually linear time, right? Because if I look at the amount of time that I'm spending in any run, it's linear. And even if I take the maximum over all of my runs, it's still linear. So this is a linear time algorithm that solves 3coloring. Of course, for normal deterministic Turing machines, I don't know of a linear time algorithm. There is a possibility that it exists. We will talk about that, but most rational computer scientists don't believe that you can solve this in linear time without non-determinism. But we don't have a proof for that. Okay. So this was just an example so that you can see the power of non-determinism. But can I define this set NP? Again, remember NP is a class. It's a set of problems. It's not a set of algorithms. It's a set of problems. I'm saying it's the set of all problems for which there is an algorithm with polynomial runtime. Okay, so this is the most common issue that I see in the exams. P and NP are classes of problems. They're not classes of algorithms. Okay, and basically the idea here is that I magically know the best algorithm for every problem. And the problem is in P if the best algorithm that I can find for it has polynomial time. Well, not the best algorithm that I can find, the best algorithm that exists, because mathematically maybe there is a good algorithm, but I cannot find it, right? Okay, and NP is the same thing, but with non-determinism. So I want to define NP in a different way. And for this, I'm going to look at the same problem. So this problem of tree coloring is in NP because I had a non-deterministic program that decided this in polynomial time. Now, again, it was linear time in the RAM model of computation. If it's a Turing machine, every time that I'm accessing this, I have to go all the way over the tape and back. So maybe my runtime is n squared instead of n. Who cares? It's polynomial, right? So here's the thing. If you want to write a deterministic program that does the same magic as the non-deterministic version, it's very hard. No one knows how to do it. But suppose that I claim that I have access to a non-deterministic compiler for C++ that can actually compile this program and it actually works for me. And suppose that you don't believe me. So you're just going to give me inputs and I'm going to tell you what my magic machine is returning on this input. And then you're supposed to verify that. Okay? Can you do the verification using a deterministic machine? So for this particular problem, the question is this. If I give you a graph and I tell you, give me a tree coloring or tell me whether a tree coloring exists, that's a hard problem. You probably can't do that. But if I give you a graph and I claim that this graph is tree colorable, you tell me prove it, and I prove it by giving you a tree coloring. And when I give you the function that is assigning colors to all vertices, you can verify that in polynomial time. Okay? So this is the kind of definition that we're going to give for NP. So I'm going to say a decision problem or a language L, again, this is a language, is in NP if, okay, suppose that I'm giving some input. Now, I don't have access to the magic non-deterministic machine. I want to only have access to a verifier. So I want to have a Turing machine that verifies solutions to this problem. So I say if there exists a deterministic Turing machine, so I don't want to use non-determinism here. And let's call this one V because it's a verifier such that, okay, what are the conditions that I want to have? My first condition is that if there is an input that is actually accepted, then you should be able to give me a witness. You should be able to give me a proof. And then this verifier should be able to verify the correctness of the proof. Okay, so for every X that is in L, there exists a proof or a witness W, and this W is also a string, such that if I give V the original input and I also give it this proof, it returns 1. Okay, so again, think of tree coloring. If there is a graph that is tree colorable, there is a proof for it, and the proof is the tree coloring itself, the assignment of colors to vertices. And there is a Turing machine V, a program V that verifies proofs. If you give it the graph and you also give it the tree coloring, it can check if it's a valid tree coloring or not. Okay. Now, of course, I don't want this verifier to accept illegitimate proofs. So I want to say that for every X that is not in L, for every input that should be rejected, there exists no witness, no proof such that V of XW is 1. Or I can also say it like this. I can say that for every proof, this V is 0. It will always say that your proof is invalid. Because of course, if my input is not in my language, I shouldn't be able to convince the verifier that it is. Okay? But now I want other things as well. I want to say that my verifier also runs in polynomial time. So I'm going to go here and I'm going to say there exists a deterministic Turing machine V and a polynomial P. And I'm going to add this third condition that for every input size n, T of Vn is less than or equal to P of n. So it runs in polynomial time. But there is one more missing piece. And the missing piece is how long can my proofs or my witnesses be? Suppose that I give you a proof that is so long, you wouldn't even be able to verify it in polynomial time, right? So I need something else here. So instead of saying one polynomial, I say I have two polynomials. Let's call it P and Q. And then here, I say there exists a witness whose length is at most Q of the length of the input. So when I'm giving you a proof, the length of that proof should also be polynomial, because otherwise, how the hell are you supposed to verify it in polynomial time if even the proof is longer than polynomial time? Again, same argument over and over again in this course. You have to read what I'm giving you, right? And here I also say that there is no polynomial size proof. Okay. This is another definition of NP. So a language or a problem, a decision problem is in NP if there is a verifier such that whenever someone claims that a particular input should be accepted, they can give a short proof, a polynomial time proof, sorry, a polynomial size proof, and then the verifier can verify that in polynomial time to make sure that it's a correct proof. So for example, 3 coloring is in NP because even if you cannot solve it in polynomial time using a deterministic Turing machine, if I claim that a particular graph has a 3 coloring, I can always prove it to you by giving you a 3 coloring, and that 3 coloring has polynomial size. It actually has linear size. And then you can verify that that's a valid 3 coloring, and the verification is done by a deterministic Turing machine, not by a non-deterministic Turing machine. And the verification also takes polynomial time. So why are these two definitions of NP defining the same class of problems? Now, so it would be interesting to prove that the language L is in NP with this definition, if and only if it's in NP with this definition, right? I'm not going to give you the proof, but I'm going to give you the main idea of the proof. So here's the thing. If I have a language in NP, it means that I have a non-deterministic program that accepts that language. So for example, for 3 coloring, I have this non-deterministic program. How can I turn this non-deterministic program to a deterministic verifier? Like, what is a kind of proof that I can give you? So what do I want to prove to you? For a particular input, I want to prove to you that there is one execution of this function that returns true. How can I give you an execution of this function? How can I prove to you that, I told you the answer. How can I prove to you that there is an execution of this function that returns true? Well, I can just give you the execution, right? I can tell you if you run this function, and let's say the first time that you get to if, you make this choice, and the second time you make that other choice, and so on. I tell you exactly which run of your non-deterministic Turing machine is going to return true. And you can verify that using a deterministic Turing machine, because you just have to verify the one run that I'm telling you will return true. You just verify that, and if it returns true, you accept it as a proof. Otherwise, you don't. So these two definitions are actually pretty much doing the same thing. You can think of it You can say a problem is in NP if there is a non-deterministic Turing machine that accepts this problem, which is the same as saying there is a non-deterministic Turing machine that has one run that accepts over every X that is in this language, right? But instead of giving you a non-deterministic Turing machine, I can give you a deterministic Turing machine that verifies. And what does it verify? It verifies that a particular run of the non-deterministic Turing machine accepts. Okay, so these two are equivalent definitions. Again, I didn't give you a complete proof, but that's the main idea behind the proof. Let's get to more interesting things. So actually, before that, one of the biggest open questions in computer science is whether P is equal to NP. We don't know. And it's crazy that we don't know because like intuitively, they shouldn't be the same. NP is the set of languages that are solvable in polynomial time, but by non-deterministic Turing machines. So I can have magic like this. I feel like this should give me more power. Hopefully I should solve more problems if I can have this kind of magic, but we don't know. So no one has a proof whether P is equal to NP or not. Actually, this is one of the Millennium Prize problems. So if you can solve it, the prize is $1 million US. And if you solve it, stay in Hong Kong because the tax bill is going to be huge other places. Okay, so we don't know if P is equal to NP. And this creates a whole theory of complexity for us, where basically when I want to tell you that the problem is hard, when I want to say that, hey, I don't have a polynomial time solution for this particular problem that you're giving me, I can just prove to you that this problem is as hard as every problem in NP. And if I do that, then I can say, well, computer scientists don't know if P is equal to NP. So I don't know if this problem has a polynomial time solution, and neither does any other computer scientist alive. Okay, so now we're going to get into that. So what is hardness? Well, in order to define hardness, I have to first define the concept of reduction. Okay, what is a reduction? Well, there's this famous joke about a computer scientist who wants to make tea, right? So they ask him, how do you make tea? He says, you take the kettle, you fill it up with water, you put it on the stove, blah, blah. And then the next question is, we've given you a kettle which already has water. How do you make tea? The answer is you empty it, and now it's the previous problem, and you apply the same algorithm. So this is the concept of reduction. The concept of reduction is that I have two different problems, let's say problem A and problem B, and I have a solution for B. And I want to say that I can use the solution for B to find the solution for A. So I'm going to somehow turn A into B. Okay, so let's do this. Let A and B be languages or problems. Again, decision problems and languages are the same thing. A reduction from A to B from A to B is a function. Okay, it's a function, let's call it f, that maps strings to strings. And the idea here is very simple. The idea is that I'm given some inputs for problem A, but I want to solve it by turning it into an equivalent input for problem B. So that's what the function f is intuitively doing. It's taking inputs of A and it's mapping it to inputs of B. Okay, now what is the property that I want to have? Well, I want to say that for every possible input X, X is in A if and only if f of X is in B. Okay, so basically I have a function f that takes inputs of A and turns them into inputs of B. Imagine that I already have an algorithm that solves B. How can I solve A? I can get any input for A, apply F. Now it's an equivalent input for B. I give it to the algorithm that I have for B. If it returns true, then the original input was in A. If it returns false, then the original input was not in A. Okay? So this is what I call a reduction. And of course, you can have reductions between any two non-trivial problems. And by non-trivial, I mean problems that don't always return true or always return false, right? Because it's just like you look at every input here, and let's say I just found one input of B that returns true and one input of B that returns false. And then I can take any input of A and I can map it to either the true input of B or the false input of B, right? So this is not very interesting on its own. It's interesting when I say that the reduction itself should also take polynomial time. Okay, so this is the definition of a reduction, but what I'm interested in is a p-time reduction or polynomial time reduction or p reduction. And basically, this is a reduction f such that there exists a Turing machine M, which basically computes f, and it computes it in polynomial time. So such that there exists, let's say, for which there exists a Turing machine M, such that on every input x, m of x is f of x. And secondly, I want to say that t of mn is less than or equal to p of n. So let's say a reduction f for which there exists a Turing machine M and a polynomial P. And by the way, when I say Turing machine, I always mean deterministic Turing machine. If it's non-deterministic, I will explicitly say non-deterministic. So, and of course, this should hold for every X and this should hold for every N. So if I have a reduction from problem A to problem B, and I can compute my reduction in polynomial time, then that's a polynomial time reduction. Now, in the rest of this course, I'm going to constantly talk about reductions, and I don't want to keep saying polynomial time. So whenever I say reduction, I actually mean a polynomial time reduction. Okay? Now, what is the idea here? The idea is that suppose I have an algorithm that solves the problem B in polynomial time. Okay? And suppose that I have a p-time reduction f from A to B. Now I can also solve the problem A in polynomial time. Because if you give me an input to A, I just apply this function f. But this function runs in polynomial time. And then it turns the input of A into an equivalent input of B. The size of that input is also going to be polynomial. And this again goes back to the fact that the Turing machine that I have for f, its space usage is less than or equal to its time usage, and its time usage is polynomial, right? So I got this input of A, I turned it into an equivalent input of B, and maybe the size has increased, but the size is bounded by some polynomial of the original size. And then I have a polynomial time solution for B. So I just apply that algorithm that I had for B. So basically, if I can reduce A to B, and if I have a polynomial time solution for B, then I have a polynomial time solution for A. Okay? Now, and we usually just show this with an arrow. So this means A reduces to B. And again, this is a p-time reduction. P-time. Now, if I reduce A to B, which one is a harder problem? No, actually, B is the harder one, right? Because if I have a reduction from A to B, whenever someone gives me a polynomial time solution for B, that automatically gives me a polynomial time solution for A too, right? But the opposite doesn't hold. Maybe I have a polynomial time solution for A, but B cannot be solved in polynomial time. The fact that I can turn inputs of A into inputs of B doesn't help in that direction. So this is the weird thing, and sometimes, again, one of the confusing issues. we reduce easier problems to harder problems. Okay, and again, I want you to think about that stupid joke that makes fun of computer scientists. So when I want to make tea and the kettle is full, I first empty the kettle. That makes the problem harder, but I know how to solve that harder problem. Okay, so when I reduce A to B, B is harder than A. Okay, based on this, suppose that I have a class of problems. So let's say this is not one of those 50-minute sessions, right? I have 20 more minutes. Okay, great. So suppose X is a class. So X is a set of languages or a set of problems. What does it mean when I say a problem is X hard? I mean that this problem is harder than everything in X. Okay, so I say the problem A is X hard if for every language L in X, L can be reduced to A. Okay, so A is harder than all the problems in the set X. And that's when I say A is X hard. So now based on these definitions, you know what NP hard means. Okay, a problem is NP hard if it's harder than all the problems in the set NP, which means that whenever I give you a problem in NP, you can reduce it to this particular problem. So for example, we will very soon see that 3 coloring is actually NP hard. So any problem in NP can be reduced in polynomial time to 3 coloring, which means that if you give a polynomial time solution for 3 coloring, you have proven that there is a polynomial time solution for all the problems in NP. And you have basically proven that P is equal to NP, which is probably not true. I don't know. Again, this is an open problem. But how do we use this in practice? The way we use this in practice is suppose you're a software engineering guy and you're working for some company and they give you a problem to solve and you're working on it for several weeks and you don't have any progress and they come to you and they want to fire you because you haven't solved it yet. And then you just show that the problem is NP hard. So you say, look, I can't solve this, but neither can any other computer scientist. We just don't know how to solve this. Okay. So this is NP hard, but now I can also define the notion of completeness, and this is actually very easy. Basically, it's this. I say that suppose X is a class, so it's a family or a set of problems, and L is a language. Or actually, let me just call it A. A is a language. We say that A is X complete if it satisfies 2 conditions. The first condition is that A is X hard. And the second condition is that A itself is in X. Okay. So what does it mean when I say a problem is NP complete? It means that the problem is in NP. So I have a non-deterministic Turing machine that solves this problem in polynomial time. But it's also harder than every other problem in NP. So I can reduce any other problem in NP to my problem. Again, as an example, 3 coloring is NP complete. Because 3 coloring is in NP, this is the proof that 3 coloring is in NP, right? And we will also show that 3 coloring is NP hard. So I can reduce any other problem in NP to 3 coloring. Okay. Now let's do some reductions. So here's the thing. I want to talk about NP complete problems, but before we do that, let's just look at our picture. So let's say I want to categorize all of my problems based on difficulty. So this is increasing difficulty. Okay. So I have a tiny few problems here that are solvable in polynomial time by deterministic Turing machines, and I call this P. And then I have another set. Maybe this set is larger, maybe it's the same set, I don't know. And this is NP. This is the set of problems that can be computed in polynomial time, that can be solved in polynomial time using the magic of non-determinism. Now, the NP complete problems are the problems that are in NP, but as hard as any other problem or harder than any other problem in NP. So these are the NP complete problems, exactly on the border. Okay. Now, everything from here onwards is NP hard. Okay, this is our picture. And again, we don't know if P is equal to NP. Now, interestingly, I also talked about P space. We know that P space is a superset of NP. So anything that you can solve in polynomial time with non-determinism, you can solve in polynomial space without non-determinism. So this is P space. And again, interestingly, I'm not going to prove this to you, but search it. P space is equal to NP space. So if you have polynomial space, it doesn't matter if you have non-determinism or not. They're the same. Okay. Anyway, and of course, if I go through this difficulty, there is some point up until that point, everything on the left is actually computable or decidable. And then on this side, I have all the undecidable problems, problems for which I don't have an algorithm. So for example, we have halting. And actually halting is very close to the edge here. Right? And in a complexity theory course, you will see different levels of undecidability. So not all undecidable problems are equally undecidable. Some are more undecidable than others. Okay. But today, we're going to focus on this tiny point here, NP complete problems. We want to see what problems are NP complete. Now, how do I prove that a problem is NP complete? Well, I have to prove two things. I have to prove that my problem is in NP. That's usually easy because I have to just come up with an algorithm that uses non-determinism and solves my problem. Usually this is not too hard. But if you forget this, you will get a 0 in the exam. And then I have to prove that my problem is NP hard, which means that I have to prove that any problem in NP can be reduced to my problem. Now that's pretty hard, right? Because I have to now reason about all the problems in NP, which means that I have to reason about all the non-deterministic Turing machines that run in polynomial time, right? But there's an interesting thing. Suppose that I have a reduction from A to B, and then I have a reduction from B to C. Remember, these reductions are just functions that are mapping inputs to equivalent inputs. And these functions run in polynomial time. They have Turing machines that compute them in polynomial time. So I can just combine them and I can have a reduction from A to C. Okay. So because I have this nice property, I don't actually need to consider every problem in NP. I can just consider another NP hard or NP complete problem. Okay. So here's the thing. Let's say I want to prove A is NP complete. Or actually, let's do it with hardness. I want to prove A is NP hard. Let's say that I already know that some other problem, B, is NP hard. Okay, what should I find? I should find a reduction from which problem to which problem? From B to A. Yeah, so just find a reduction from B to A, because that would prove that A is harder than B, and B was already NP hard, so B was harder than everything in NP, so A is harder than everything in NP. That's the idea. And of course, if I want to prove that A is NP complete, I first have to find a reduction like this from a problem that I already know is NP hard. to show that A is NP-hard. And then I have to also show that A is in NP. Again, don't forget this second part. Like, so many people will forget this in the final exam, I'm sure about it. But when we talk about completeness, and especially NP completeness, you have to show that your problem is in your class. Your problem is actually in NP. It's very easy to come up with problems that are not in NP, but are NP hard. Halting, right? Okay. Great. Now, I'm going to give you a theorem, and you're just supposed to believe me in this course because the proof is too long. Okay. And this is the theorem that we just believe. And this is that CNF SAT is NP complete. Now, what is CNF SAT? CNF stands for conjunctive normal form, and SAT is satisfiability. So the idea is this. Let's say I give you a formula. The input is a formula in conjunctive normal form over some variables, over, let's say, x1, x2 to xn. Okay. So for example, I can have a formula like this: x or y or not z, and y or z, and x or w or y. Okay. So my variables here are x, y, z, and w. And the things that I have here, I have a bunch of literals. So this is called a literal. It's either one of my variables or the negation of one of my variables. This is also called a literal. Okay. And then I have a bunch of clauses. So this whole thing is called a clause. And a clause is just the or of some literals. Okay. And then I have my whole formula, which is just the and of some clauses. Okay. And the output should basically tell whether this formula is satisfiable. So let me call this formula phi. Output should be 1 if phi is satisfiable. Which means, so imagine that all of these variables are Boolean variables. They can each take true or false as their value. Can I somehow assign true and false to x, y, z, and w so that the overall formula becomes true? That's the question. And you should return 1 if it's satisfiable. You should return 0 if it's not satisfiable. Okay, this is called CNF SAT. Great. Now, why is it NP complete? First of all, why is this in NP? It's in NP because if I claim that a particular formula is satisfiable, I can always prove it to you by just giving you the assignments of true or false to the variables. And then you can just plug it in and you can verify if it ends up being true, right? And evaluating a formula, if I give you all the values for these Boolean variables inside it, that's going to take polynomial time. So if I claim a solution, I can give it to you and I can prove it to you, and the verifier, like you as the verifier, will take polynomial time. So it's in NP. Now, why is it NP hard? That's the part where you have to trust me, it is. But if I want to just give you some intuition for why this is the case, the intuition is that what is the general problem in NP? The general problem in NP is that I give you a non-deterministic Turing machine, and I ask you, is there a run of this Turing machine that returns true? And you can write that problem as a formula of this form. Now, writing it as this kind of formula, it's really complicated and unnecessarily complicated. Just search it on Wikipedia, you'll see it. It's like a 5-page proof, but you can do this. So it handles everything that you can do with a Turing machine. Okay, so I know that this particular problem is NP complete. I want to use this to prove that other problems are NP complete. Okay, pay attention. This is definitely going to be on the exam. Not this particular reduction, but of course other reductions. So first, I'm going to look at the problem of 3-SAT. So 3-SAT is the same as CNF SAT, except that every clause has only 3 literals. Okay, so my input is a CNF formula phi with 3 literals per clause. And my output is basically the same as before. Is it satisfiable or not? So CNF SAT, sorry, 3SAT is a special case of CNF SAT. And it's a special case where my formulas have clauses that only can have 3 literals. So I can have X or Y or not Z. And let's say X or W or Z and something else. But in every clause, I always have 3 literals. Okay. So this is a special case of the previous problem. It seems like the previous problem should be harder. And yes, you can definitely have a reduction from 3SAT to CNF SAT, and the reduction is just the identity function. Don't change anything, because every input here is a valid input here and has the same answer. So CNF SAT is definitely harder than 3SAT, but the interesting point is that we want to prove the opposite. We want to prove that 3SAT is also harder than CNF SAT, which means that they're equivalently hard. Okay, so basically the idea here is that I have to find a reduction from general CNF SAT to 3SAT. So I've given you a general formula, rewrite it in polynomial time such that every clause has only 3 literals. Okay, how can I do this? Well, I look at my original formula. If I have a clause that already has 3 literals, I'm happy. That's fine. If I have a clause that has less than 3 literals, so let's say, for example, I have something like this, X or Y. Okay, what can I do? How can I make this into 3 literals? Well, just repeat one of them, right? So if I get X or Y, I would turn it to X or Y or Y. Problem solved, right? What if I have a clause that has more than 3 literals? So let's say I have a clause like this, X or Y or not Z or not W. Okay. Now this is a problem, but I can solve this by introducing a new variable. What do? I want to take this part or any two of them. Let's say I take this part, Y or not Z, and I give it a new name. I call this one T. Okay. So now, after my reduction, I will have this clause, X or T or not W. But I have to also somehow enforce that T is the same as Y or not Z. Okay? How do I enforce that? Just give me a clause or several clauses with 3 literals each that ensure that T is the same as Y or not Z. Maybe it's easier if I do it with variables that are not inverted. So let's say I take these two to be T because I can always add negation wherever I want, right? And then here, when I'm reducing, I will have T or not Z or not W. And I want to add some extra constraints, some extra clauses that make sure that T has the same value as X or Y. What? X or X or Y. No, well, I have to somehow use T, right? Not T or not X or not Y. Would this work? So here's the thing. If X or Y is true, it means that one of them is true. Okay? So what should I assign to T? No, the problem is that you just know that one of them is true. Maybe you don't know that both of them are true. Right? So we use exclusive form. No, you can only use or because you have to be in CNF form. right? So you're in 3 sets. You have a bunch of clauses. Each clause is the OR of 3 literals. And your whole formula is the AND of the clauses.
I think we have to put 2.
Okay, let's put 2. What do you want to put?
Not T.
Okay.
I'm thinking of like implication.
Yes, that's actually a good way of thinking about this. So here's the thing. If T is true, what do I want to have? I want to say that either X or Y is also true. Okay, so if I have T or something, what should I put here? Okay, let's go your systematic way. I want to have T if and only if I have X or Y. What does this mean? This means that I want to say that T implies X or Y, and I want to say X or Y implies T. Let's write each of these separately. If T implies X or Y, what does that mean? What is this equivalent to? No, X or Y or not? Okay, so I have X or Y or not T, right? Okay, I'm happy about this one because this one is now a valid clause in my 3 sets. Okay, how about this one? What is this equivalent to? Yeah, so here I have T or not X or Y, right? So I'm not happy with this because this is not in the format that I wanted. But I can simplify this. So what is this? This is T or not X and not Y. Okay. So I can write it as T or not X and T or not Y. Okay. Now I have to also, again, I need 3 literals per clause. So I'm just gonna write it as T or not X and T or not Y. So I'm going to add this clause, and this one as the translation here. And of course, I will have the original clause as well. But the important point is how much time is this taking? Is it taking polynomial time or more than polynomial time? I'm basically taking a clause, and let's say that this clause had a bunch of literals. Let's say it had k literals, right? I'm adding 4 clauses to reduce the number of literals to k minus 1. And I'm just going to do this until the number of literals is reduced to 3. And if I do that, it's actually linear time. It's not only polynomial time, it's linear time. So the important point is that if I give you any stat formula, you can rewrite it as an equivalent 3-sat formula. And that rewriting takes polynomial time. So I have a polynomial time reduction from sat to 3-sat. Now, sat was NP hard. So 3-sat is also NP hard. 3-sat is also in NP because if I give you a formula like this, you can just write a magic program that guesses what to assign to every variable and then just checks that the formula is satisfied. So because 3-sat is in NP and it's NP hard, 3-sat is NP complete. Okay. And actually, 3-sat is the main problem that we're going to use in all of our future reductions. So again, remember when I want to prove that something is NP hard, all I have to do is to reduce another NP hard problem to my current problem. Usually the problem of choice is 3-sat. So usually this B that we use here is 3-sat. You can choose any NP hard or NP complete problem that you want. But again, in practice and also in the exams, use 3-sat. 3-sat is easier. Okay, tomorrow we're going to see a ton of reductions. We're going to see like many different problems that are NP complete, and we're going to see a bunch of reductions between them.